Continuing on from part 1, I will be carrying out a composite video modification on a ZX-81. But before we get to the modification itself, let me give you a brief overview of what I will be doing and why. If what we want to do is to send the composite signal produced by the ULA to the television, the first thing one would think of is to just put a wire between the ULA, the corresponding pin, and the television, and presto, we are done. Unfortunately, this would not work. The television would draw too much current from the ULA, a current level that the ULA wouldn't be able to provide. And in the best case scenario, you would end up with an image that doesn't work. You wouldn't have a proper image. Or in the worst case scenario, the TV would pull so much current that the ULA would fry, attempting to provide all that current. So this doesn't work. We need a buffer. And a buffer is something in between, which is itself connected to the 5-volt power rail, which can provide large currents. And this something in between, this buffer, would provide the current levels required by the television. And somehow it would encode here in this current the same information available here in this current coming from the ULA, which captures the video information. So the video information would be mirrored here on the other side of the buffer, but at much higher current levels. That's what we need. The simplest way to do that is by using a little transistor, in this case an NPN amplifier transistor, and a resistor. And here is how it works. We will connect the pin of the ULA producing the composite signal to the base of the transistor. And then from the emitter, we will hang a 100 ohm resistor to ground. And once the ULA produces a voltage potential here, it will induce a small current flowing from the base to the emitter of the transistor through this resistor and to ground. It is the variations of this current, or the variations of the corresponding voltage level here, which contain the video information that you need to send to the television. But in this case, it's not going to the television, it's being drained to ground at small current levels, so the ULA is protected. But how do we get that information then to the television? Well, that's the nice thing about a transistor. Once a current is flowing between base and emitter, it will induce a mirror current from collector to emitter, and the collector is hanging from the 5-volt power rail, so this current can be very large. In the case of this specific transistor, the BC337-40, it's about 100 times larger, higher than the small current flowing from base to emitter. But it mirrors the small current. The variations of the small current will be mirrored in the variations of the large current, and therefore the large current here will contain the video information to be displayed. Now, in principle, if you don't put any resistor here, this current will flow straight to ground and there will be no signal for the television, and moreover, you would fry the transistor. But because there is a resistor here, this resistor will oppose the flow of this large current to ground. And it will force a buildup of electric potential here on this side of the transistor, which will then force the current through this resistor. And it is this electric potential that will also contain the video information coming from the ULA, because it will be proportional to the large current, which in turn is a mirrored version of the small current. So this point here, the voltage potential on the emitter will contain the video information. So if we tap it here and send it to the television, we should have a good image in a buffered way, because it's not the ULA providing the current that will flow here, it is coming from the collector, which is hanging from the power rail. That's the buffer we want. Now, it is possible that too much current will flow through this line here instead of going to ground, because this is a 100 ohm resistor, and modern televisions, composite signal input has a total impedance of about 75 ohm. That's the equivalent resistance of the television. 75 is lower than 100, so the current will flow preferentially in this way and less preferentially in that way. They will flow through both lines, the current, but more current will flow that way, and that could lead to a too bright image, too oversaturated, where you don't get to set the contrast right, and you would basically not see anything. It would be all glaring white. If that happens, and that depends on the specific television you're using, if that happens, there's always an option to add a little resistor on this line here to balance out these two lines. So less current flows here and a little more flows to ground. This is what we are going to try and build. I will start with just the transistor and this resistor. I will see how bright the image is, and if necessary, I will add just, by trial and error, I will add a little resistor here until I get a nice image. I am using a BC337-40. This is probably an overkill for this application. Well, not probably, it is an overkill. This is a very robust transistor. It will last a long time, and it can take up to 800 milliamperes of current flowing from collector to emitter, which is much more than what I need for this specific application. But yeah, I rather exaggerate and be conservative than the other way around, and these things are very cheap anyway. So let's go ahead and do this mod. Okay, the composite modification has been done. Here is our transistor, the collector connected to 5 volts, the base to the composite signal, the emitter to the RCA jack, which also has a 100 ohm resistor connecting it to ground via the CAN of the RF modulator. So I've connected now my composite cable, so it's no longer the RF input of the TV, and let's see if it works. It does, but the cursor is pretty light. There is very little contrast because the cursor is very light. I think we need to add another resistor to soften a little bit the brightness of the image. There it is. And the emitter connects to this joint here. On the one side, it goes via the 100 ohm resistor to ground and via the 33 ohm resistor to the RCA jack. Okay, I am all set to test it. Fingers crossed. 3, 2, 1. Yeah, much better. The cursor is now clearly visible. I think the rest I can adjust directly on the TV. Yes, that will do. That will definitely do. So there we are. And so this doesn't look ugly. I made it in such a way that, one, it's reversible. So somebody can take this stuff out and reconnect to what was there, and then you would have an RF modulator again. And I also made it so I could close the lid with luck. There we go. Yeah. People will be none the wiser to notice that there is a modding here, because from the outside it looks the same, and yet composite is on the screen. I wanted to show you the clock signals, because the ULA generates a clock signal based on this ceramic oscillator here. It puts out the signal through a pin on this side of the ULA, which then goes through some circuitry for buffering and signal shaping, and gets into the CPU, and that's what makes the CPU tick, literally. So I've rigged just two little wires here to the respective pins where the clock is, on the CPU and on the ULA, the CPU in green. And I wanted to show you on the oscilloscope how it looks like. So you see the difference. Okay, let's turn it on. I'll even connect the TV to make sure that it's working properly. Yes, there we go. So that's what you see there. In blue is what the ULA is putting out. It's a shark fin signal, and gets buffered and improved in shape a little bit. And you see this is closer to a square wave here. There is some overshooting here at the bottom, but that's no problem. The thing just cannot eliminate all the higher frequency components, so you get these little artifacts. Okay, the next steps are to swap out these 3.5mm jacks for gold-plated ones, so I have optimal audio quality to upload data and then store data with this computer. And since I will have the desoldering station on, I will also replace the linear voltage regulator with this DC to DC converter, switch mode DC to DC converter, and then I will lose the heat sink as well. And I will change these two axial electrolytic capacitors here just as preventive maintenance, so they don't leak. They are not critical in this architecture anyway. One is connected to the 9-volt power rail, and the other one I think is associated with the reset circuitry, but I'll just exchange them. And then I will test it before I do further steps. So let's get going. Okay, here we go. We have now a buck converter, a DC to DC switch mode voltage regulator, and we have golden plated 3.5mm jacks now. Okay, the board is recapped. Should still work. Let's see. And it does. Let's check the voltage that is being put out by the new voltage regulator, switch mode voltage regulator. So the input voltage should be 9 volts from the power supply, the external power supply. So 8.97, that's as close as it gets. Now to access the 5 volts, I have to look underneath. So this goes here, and I'll probe the pin underneath. 5.010, that's very good. Okay, next step, I want to do a CPU upgrade. Well, not really an upgrade. I want to put a new Z80 from Zilog here. These chips, these CPUs are still made today in modern CMOS technology, so there is little reason to use, continue to use the old Z80s. They are fragile, they pull a lot of current compared to the modern ones, and the modern ones, you know, cost a couple of euros. I have a bunch of them, so I'm going to desolder this, pull it out. I will keep this old chip in my stash of historical parts, and then I will install a socket, a precision socket in here, and a new CMOS Z80. So let's get going with that. Now, this time I'm going to indulge myself. I'm going to use this, which is completely unnecessary in a computer, little computer like this. This is a gold-plated precision socket. It will last forever, and there will be very little noise. It doesn't oxidize. Totally unnecessary in a ZX-81. But you know, this is special. This was my first computer. It basically defined my life as it has been until today. I've worked in the computer and high technology industry and the semiconductor industry for more than 2 decades now. So I am going to use this one. Alright, it's unnecessary, but it will be a gold pimped ZX-81. Okay, here comes our Z80. And it is in place. Okay, now that the new CPU is in place and it's easier for me to probe the terminals here, the pins on the socket, I'm not going to use the technique I've shown you before, you know, installing a wire to be safe. Do what I say, don't do what I do now. I'm going to probe the legs directly, because I want to show you several signals here on the pins, so it's not practical to solder a little wire every time. Anyway, I don't think I'm going to make a mistake and short anything out. What I wanted to show you, let me turn on the computer. It is on. Remember, we talked about the data bus, the address bus as well, but mainly the data bus in the ZX-81 being split by an array of 8 470 ohm resistors, and that was a way to allow the ULA to always have priority, to always be able to override the data bus towards the CPU. So the CPU is always under the control of the ULA. It will do what the ULA says, even if there is something else on the data bus. Well, that is an analog solution to a digital problem. It works, it's very cheap, but it's not really the way anybody would do it today. And I want to show you the price of that. So if I probe a address line here on the CPU, like this pin here is address line 10, and you can see there on the scope that we have a well-formed digital signal. It's either 0 or 5 volts. Yeah, there is some high frequency oscillations there that are not filtered out, but it's a well-formed digital signal with valid, clear logic levels. This is address line 9. You see it's the same kind of signal. Address line 8. It's also a well-formed signal. But when it comes to the data bus, which is here on the other side, I will probe just some of the data lines for you to see how they look like. Look at this. This is a mess. There are all kinds of levels here. It's not only a clear 0 or a clear 5. Actually, it doesn't even build up to 5. It builds up to 4 volts. And it's a mess. I'll probe another data line. No, this is not the data line. This is the 5 volt input. This one. This is another data line. This is yet another data line. Now, this works. The computer will interpret it digitally. So if the voltage level crosses a certain threshold, it's 1. If it doesn't cross that threshold, it's 0. So despite of the mess you see here, it still functions. It still works because of this digital interpretation of this analog signal. Okie dokie, what I want to do now is to replace these two memory chips with a 32 kilobyte memory chip. We'll be able to address 16 of those. I just have to find, yeah, here it is. So I'm going to replace these two with this, and if you pay attention, here are the outlines in the silkscreen marking for these two chips here in yellow you see around, but you also see another outline here in yellow for a bigger chip, this one here, and it will fit this one will fit in that outline perfectly, although the pinout of this chip here was not taken into account when they designed the board, when they designed the traces that come to the pads where this chip will sit. So we'll have to make some modifications. Okay, so the first job now is to remove these two little memory chips in there, and also open up these vias here so I can put a socket, and now we will do that with the soldering station. Okay, so this is the chip that normally would come on this socket here. Sinclair had two possibilities. Either you would use two chips of 1024 words of 4 bits, so together they would form a byte, 8 bits, and then you would have 1 kilobyte, or you would use one chip of 1024 words and 8 bits, and that's how you would get 1 kilobyte in an alternative way. This 1 kilobyte bit did not use the top 4 pins here. These 2 lines here on the top were not used, although the board has some traces going to these pins. So they anticipated something that was not done. So this is the one chip that would come in here, leaving these 4 pins unused. And this is the chip I want to put in there. Now I filled with blue here the pins that are the same on this chip and this chip. And then I know that the board was made for this chip, so the board will be wiring all these signals here in blue to this chip. And this one here I checked with the multimeter. These 2 bits here, which are pins here, which are not in the old chip. So there are 5 pins that I have to wire up myself with bodge wires to some other place on the board. It's this, 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 and this. So now the job is to find where I can bodge wire these 5 extra pins to. I will lift them so they don't go into the socket. I'll show it to you in a moment. I will lift them, making them horizontal instead of going vertically into the board. And then I will solder a little wire on them and wire that up to some other place in the board, which I have to find now. I have to find where address line 10, 11, 13, 12, and 14 are. I know they exist. I know they are on the board because this edge connector here was made for a memory expansion of 16 kilobytes. So the board has to route the extra address lines needed to address 16 kilobytes instead of 1 kilobyte. So they have to be available somewhere here. And I see there are a lot of pads that are unused. Worst case, I will just wire them up to the pads here right next to the edge connectors, but I'll try to find them somewhere closer by. We'll see.